The electron cloud. The electron cloud is the region around the nucleus where we have the greatest probability of finding the electrons. There's no hard, rigid shell to the electron cloud. It's just much like a cloud in the sky. It just eventually kind of tapers off and gets less and less probable to find the electrons. Region around nucleus where it is most probable to find electrons. We're going to talk all sorts of details about the electron cloud. It's much more complicated than what we've talked about so far, and even this version that we're going to learn this year is actually much simplified. We get more details when we take chemistry. The electron cloud is broken into energy levels. And energy levels are what you see down below. Keep in mind the atoms are 3 dimensions, so that means that each energy level is actually a sphere and not a circle. That's one of the very common misconceptions, is that an energy level is just a circle, like an orbit around the sun. These are not orbits. These are energy levels. So energy levels are one of our vocabulary words. So an energy level is a specific region from the nucleus where electrons can be found. We have to date, currently, we have 7 energy levels that we know exist. They are numbered 1 through 7. Each energy level has a different energy associated with it. The energy level closest to the nucleus requires the least amount of energy, and the energy level farthest from the nucleus requires the most amount of energy. Each energy level has a specific amount of energy requirement, I think is the best word for that. Meaning, if you have a lot of energy, then you will move to a higher energy level. If you have less energy, then you will be at a lower energy level. Energy levels closer to the nucleus have lower energy requirements. Energy levels are a lot like stair steps, in that you can be only on a whole number. There are no half numbers of energy levels, kind of like when you're climbing stairs. You can be on the first step or you can be on the second step, but you cannot. So you can be on the first step, you can be on the second step. However, there's no like 3.5 step, right? You can't, and if you try to step there, you'll likely, I don't know, trip and fall on your face or something. That's when you stumble and fall. Energy levels are the same. You only have a whole number. You have to be either on the first or the second or the third. There's no between level possibility for the electron. Different amounts of energy means a different energy level. The closer you are to the nucleus, the lower in energy that electron is. The example that I have drawn right here, we're going to start with the nucleus and figure out what kind of atom we have so that we know how many electrons we need. The pink are the protons, so I'm going to count protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 protons, which tells us that this is an atom of magnesium. And if it has 12 protons, it also has 12 electrons because the positive charge equals the negative charge. So protons equals electrons. We not only have a specific energy associated with each energy level, but each energy level can only hold a specific number of electrons. Number of electrons per energy level changes. And so I'll walk you through that as we fill in this for magnesium. So the first energy level, here's my electron right here. The first energy level has a total of 2 electrons in it. And they will be as far away from each other as possible because they are negatively charged and negative charges repel each other. So the first energy level has 2 electrons. The second energy level then has a total of 8. So 1, that energy levels are spheres, so I'm trying to spread them out so they're evenly spaced. But again, they would occupy regions above and below and in front of and behind and all of those. So the second energy level has 8 electrons. So far we have pictured 10. Since this is magnesium, we need 2 more electrons. And so the next 2 would be in the third energy level. Now in this case, the third energy level is not completely full because the third energy level can hold more than 2 electrons. But for magnesium, we only want a total of 12, and so we have all 12 pictured. There are the energy levels that exist in each magnesium atom. We would need an atom larger than magnesium if we wanted to fill the third energy level. So if, for example, we did argon, and I'm going to do this one a little faster. So argon, we just put argon in the center, and we're going to fill electrons. Argon has 18 electrons, and again, I know that by looking up argon on the periodic table. We're going to follow the same pattern though. 2 in the first energy level, 8 in the second, and so that gives me 10, and then I'm going to go to the third, and I need 8 more. 2, 3, 4, 5, 6, 7, 8, 9, too many. There we go. There's the 18 electrons that would be in argon. So there's 8 in the third energy level there, but that's still not full. So let's keep adding electrons. So let's get something even bigger. Let's go really big. Let's do 10, which is SN. 10 has 50 electrons. So we have 18 to start with. We're in the third energy level, and the third energy level can hold a maximum number of electrons, or its maximum number of electrons is 18. I'm going to put 18 in my table over there. So I have 8. Right now, I'm going to add 10. Okay, so that gives me a full third energy level, but I need to keep going because I want 50 electrons, and right now I don't have 50. The fourth energy level can hold a total of 32 electrons. So I have 10, 28 so far. Okay, that is 50 total electrons, so I have made my atom of tin, 50 dots for 50 electrons. The first energy level has 2 electrons, the second energy level has 8, the third energy level has 18, assuming that I counted correctly. Anyway, the fourth energy level is not full, but it can hold up to 32. To continue our table, the fifth energy level holds 50 electrons, the sixth holds 72, and the seventh holds 98. Currently, we do not have any more energy levels. It maxes out at 7, but that could change in the future. Okay, so this picture that we have drawn here is, kind of tedious, takes up a lot of room. There's a lot of counting involved. Not really the greatest. This picture is used to show energy levels, but it's really very cumbersome. We want to focus our attention on what we call valence electrons. And these are the outermost electrons in an atom. So that means they are in the highest energy level, which also means they have the most energy. In that atom, anyway. And focusing only on the ones that are on the most outside is very useful because they are the ones that are involved in all of the chemical reactions. The inner electrons do not get very much action. They don't really go anywhere. They don't do a lot of changing. We're really, really concerned with the outermost electrons, which we call the valence electrons. So we take this big kind of messy diagram that I have drawn here, and we simplify it into these guys, what we call electron dot diagrams. And it is all tied together on the periodic table. And I did plug in some of the elements to help us kind of as a guide as we talk about electron dot diagrams. So first of all, what is an electron dot diagram? The electron dot diagram uses the element symbol and dots to represent electrons. But we are not doing all of the electrons. We are only doing the valence electrons. Represent the valence electrons. The electron dot diagrams are based on this big crazy picture that I have drawn up here. We eliminate a lot of the mess. So some things to get you started. We're going to start small. We're going to look at boron. Boron has 5 electrons. So if we do the energy levels, we're going to start this way, and you'll see why. We're going to fill them lowest to highest. So first energy level gets full, and then we go to the second energy level. And the second energy level only has 3 electrons in it because we only need a total of 5. So 1, 2, 3, 4, 5. So we don't need that one at all. And we are only going to focus on the valence electrons, those on the outside, which means that boron has 3 valence electrons. And once we know that, we can do the dot diagram. So the dot diagram is the symbol and then 3 dots. And this is the magical piece that is the most important thing ever, the dot diagram. So boron with 3 dots. Again, we don't need this one at all. It's not very useful today. All we're doing is figuring out, or we use it to figure out how many valence electrons there are. Okay, let's do another. We'll start simple. Again, let's look at neon. So we're going to start here. Again, 2 electrons, and then 8. 1, 2, 3, 4, 5, 6, 7, 8. I forgot to see, we want 10 electrons total. Again, this number, the 10, I know this because I looked it up on the periodic table. The number of electrons is equal to the atomic number. So I have 10 electrons pictured. I then can do the dot diagram. I draw its symbol and then 8 electrons. I'm only doing 8 because there's only 8 in the outer energy level. Valence electrons only. So there's 8 there, so I do 8 dots. Let's do one more example. Actually, let's do the example we did up above so I don't have to redraw anything. Let's look at magnesium, which is this one right here. We're going to go write the symbol. We already have the dots drawn. We want the electrons in the most outside energy level, which is 2. There's 2 in the third energy level. So there's the dot diagram. Magnesium with 2 dots. Some things to note that maybe you've noticed. If you haven't noticed, please notice now. There is only 2 electrons per side. We kind of end up drawing a little box around the symbol to indicate that there are 4 sides. There are no pairs until each side has 1 electron. So this would be a good example if we looked at nitrogen. Nitrogen is going to end up with 5 outside electrons, 5 valence electrons. So a good way to do that is to draw 1 on each side. So 1, 2, 3, 4, and then 5. So we have 1 side that gets a pair. It does not matter which side ends up with that pair. You can draw it wherever you want it, but that is one example of this rule. No pairs until each side has 1 electron. And we have a maximum of 8 electrons, no matter what. We are going to follow the octet rule to a T. The octet rule states that each atom is stable atoms are stable with 8 electrons in their outer energy level. And so when we did the example of, where are you, neon, this is the most electrons that we can have. So this is what it would look like. 4 pairs, 2 dots per side. That's the most electrons that you can have. This last one is probably a given by now, but the symbol is what we put in the middle. So a few notes there to always follow when we do electron dot diagrams. There is a pattern on the periodic table. Hydrogen is kind of obvious because it only has 1 electron. So it's only got 1 dot. Helium has 2 electrons, so it's got 2 dots. We did neon already, so we know that it has 8 dots. Magnesium, we did magnesium up above. We did boron, has 3. What else have we done? Boron, neon. What was this over here? Tin. I don't know if we want to put tin on there. But anyway, we have a connection. And this is kind of from last week. Elements in the same group or family, which is, of course, a vertical column, have the same number of valence electrons. And this is the reason why they have the same properties. This is what I was writing up here, which is why they have the same properties. But again, the periodic table can be very helpful because if we know how many valence electrons one thing has, we know what they all have. So if the first column, all is going to have 1 electron. The second column is going to have 2 electrons. The third through the 12th columns, they are the transition elements, and guess what? They have 2. There are exceptions in here, but for right now, we're going to ignore that they exist. We will learn about them later. So we do have some exceptions. I know about that. Hold your horses on Google, people. And then the 13th column has 3 electrons, just like boron has. The 14th column has 4 electrons. And I know it's deceiving to look at 10 up here, and you're like, but what? There are way more than 4 in the outside energy level. I get that, but this is one of the reasons why when we get to these elements down here, our textbook does us a disservice and oversimplifies it. So I hate to say this, but you're going to have to trust me on this for right now. Simplified. Tin has 4 valence electrons. Something in the 15th column is going to have 5. 16th is going to have 6. Again, this is a perfect example. You don't double up until every side has just 1. The 17th column is going to have 7. And then the 18th column has 8, except for helium. It only has 2 because it only has 2. The rest of them have 8. So that should help you a lot when you are answering the questions over dot diagrams. So the electron cloud is much more complicated than this, but it's a start. It's very much a start.